You'd think, with its billions of bits in its memory, that computers would be incredibly accurate, and they are for the most part. The problem is when we start trying to represent things like floating point values in a binary system, decimal floating point values in a binary system, sometimes we lose some accuracy. For example, this piece of JavaScript is meant to display the value 5.3 with 20 digits to the right of the decimal point. And as you can see from the output, well, we kind of missed the mark. It's close though, right? Well, in some industries, close isn't good enough. For example, in the finance industry or in manufacturing where tolerances are really tight, we need to have something that's incredibly accurate, very accurate in the decimal sense of the word. Now, whenever we try and display a number, or when we try and represent a number, for example, let's say 94 base 10, in binary, an unsigned binary. Let's see if I can get this pen to work. Remember that if I've got 8 bits to represent the value for 94, the decimal value 94, each one of those bit positions represents a different power of 2, starting with the least significant bit, which is 2 to the 0 or 1. Then the next bit position, which is 2 to the 1, which is 2. And then we have 2 to the 2, which is 4. And then we have 8, 16, 32, 64, 128. All right. Now, if we were to try to represent 94 using this 8-bit unsigned binary number, well, the largest power of 2 we can pull out of this is 64. So there is no 128, but we do have a 64. Now, when you pull 64 out of 94, we get 30 left over. The next highest power of 2 in 30 is 16, which means we don't have any 32s. 30 minus 16 is 14. We pull an 8 out of that. We have 6 left over. Pull 4 out of that. We have 2 left over. Pull out another 2, and then we have 0 left over, which means we have all the components that is necessary in order to represent 94 in unsigned binary. Now, there's another way to represent this. And the other way of representing this with 8 bits is to say, okay, 94, what I can do is I can take certain number of bits to represent the number of ones we have. Remember, we're trying to represent this in base 10, and we're trying to use binary to represent a base 10 number. So what we do is we reserve some of the bits to represent the ones place. Then we reserve some more bits to represent the tens place. And if we had a hundreds place, we'd have to add some more bits to show what the hundreds value is. So how many bits do I need to have, or do I need to reserve in order to represent a value that could be visible or could be present in the ones place or in the tens place or the hundreds place and so on? Well, we're looking at trying to represent values from 0 up to 9. 0, no problem. 1 bit can do 0. But how many bits does it take to represent 9? Well, 9 is actually 8 plus 1. So it requires all those 4 bits in order to represent a magnitude of 9. So the idea is that instead of using 8 bits in unsigned binary to represent this 94, instead what we will do is we will break this into a tens place and a ones place. So there's the tens place, and then there's the ones place, all right? And so now these 4 bits are meant to represent the number 4. They're simply containing the value that is in the ones place. These 4 bits are going to contain the number 9 in order to represent what's in the tens place. Now remember, from the last lecture, we were talking about hexadecimal and using the patterns of ones and zeros that are available in a nibble, 4 bits, in order to map that to a value from 0 all the way up to F. Those 16 different patterns of ones and zeros representing from 0 to 9 and then A through F, those 16 symbols. And that gave us the ability to convert to hexadecimal. But what we're going to do now is take a binary nibble and come up with what we're referring to as a BCD value. BCD, that's an interesting term. It stands for binary coded decimal, BCD. Now, BCD, the importance of BCD is that it allows us to accurately represent decimal values inside of the computer. So, this table, what I'm going to do is I'm going to show just the first 10 values that we can have with a nibble. So we start out with 0, 0, 0, 0, which is in decimal is a 0, right? And we have 0, 0, 0, 1, that's a 1. 0, 0, 1, 0, 2. 0, 0, 1, 1, that's 2 plus 1, that's 3. 0, 1, 0, 0, that's 4. 0, 1, 0, 1, 4 plus 1, that's 5. 0, 1, 1, 0, 4 plus 2, that's 6. 0, 1, 1, 1, 4 plus 2 plus 1 is 7. And then we have 1, 0, 0, 0, which is our 8. And then 1, 0, 0, 1, that's our 9. And so this gives us the nibbles that are required in order to represent each one of the decimal digits. So, for our value 94 now, instead of representing it in unsigned binary, we're going to represent it in BCD. And to represent it in BCD, first of all, let's take a look at the ones place. The ones place has a 4 in it. So we go through our table, we find the 4. This is 0, 1, 0, 0. So 0, 1, 0, 0. Now, for the tens place, we have a 9 in it. And that 9 is 1, 0, 0, 1. So 1, 0, 0, 1. Now this is a really important concept. What we're looking at here is the fact that 94, depending on how we have told the computer to interpret the bits, could be represented as this pattern of ones and zeros, 0, 1, 0, 1, 1, 1, 1, 0. Or it could be representing it as BCD, which would be 1, 0, 0, 1, 0, 1, 0, 0. All right? Now, real quick, if I'm looking at this way of representing something in BCD, what's the largest value I can possibly represent? Well, 99. That's the biggest number I can represent. So I can go from 0 to 99 in BCD. In this unsigned binary, I've got a lot larger range. With those 8 bits, I can actually represent up to 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1, or 255. So BCD is only capable of representing, well, heck, not even half of the numbers that we can represent in unsigned BCD. But the benefit is that we can actually do a quick translation. In other words, it's really easy to say, oh, 94. Pretty easy. So translation is quick. In addition, decimal values kept incredibly accurate, all right? Because it's accurate with respect to how human beings count in decimal, right? Now, one more thing about BCD. Whenever we're talking, and this, by the way, is actually referred to as packed BCD. There are other forms of BCD which allow us to do slightly different representations. Some take 6 bits, some take 8 bits per digit. We're looking at just the ones where we're taking 4 bits per digit. Now, how do we represent a positive or negative number? Well, look, there are a bunch of missing values here, right? In other words, well, not missing values, but available nibbles here that we don't use for a BCD value. 2 of them we're going to use to represent a plus sign and a minus sign. One of them is going to be 1100, a hexadecimal C. This is a plus sign. The other one, 1101, that one is going to be the minus sign, a hexadecimal D. Now, unlike humans, which we tend to put our plus and minus signs at the beginning of the number, what we do whenever we're looking at BCD is we're actually going to tack that nibble onto the end of the number. So for positive, and I try not to run out of room here on the board, but for a positive 94, we have the 9, 4, and then we have to take the plus sign, 1100, and tack it on the end in order to complete our packed BCD. Now, you may think, well, heck, I'm not going to worry about this. I don't need to worry about this. Let's just let the computer do this. Well, every computer, every piece of hardware that has a clock in it uses something called a real-time clock. It's actually a chip that is part of, or a circuitry that is part of your computer. Most BCD clocks actually store their values, their time in, most real-time clocks store their values in BCD. Why? Well, let's take a look at this. Hours, right? Minutes, and seconds. Let's just look at the time for now. Each one of these is represented using, well, hours. That goes from 1 to 12, or military time, 1 to 24. Minutes, 0 to 59. Seconds, 0 to 59. Month, 1 to 12, right? Day of the month, 1 to 31. These are all values that are limited. They're less than 99, so they fit easily into a single byte. So you have 2 nibbles for hours, 2 nibbles for minutes, 2 nibbles for seconds. Now the way this works then is that you simply read your BCD value from the real-time clock and just look at the individual digits, the individual nibbles, in order to get your tens place and your ones place. Why do they do it this way? Well, they do it this way because of the ease of conversion. Simple circuitry makes it quick and easy to convert between decimal and binary.